In the arrangement shown in the figure given below, the mass of the rod capital M exceeds the mass small m of the ball. The ball has an opening permitting it to slide along the thread with some friction. The mass of the pulley and the friction in its axle are negligible. At the initial moment, the ball was located opposite the lower end of the rod. When set free, both bodies began moving with constant accelerations. Find the friction force between the ball and the thread if t seconds after the beginning of motion, the ball got opposite the upper end of the rod. The rod length equals small m. So over here the things which we have is, the first thing is the thread is not tied with small m. So if it is not tied with small m, so there only the classification that can happen over here is that the mass small m is sliding along the length of the thread. So we say that there is a frictional force F which is acting in the upward direction as the mass m is sliding along the thread. The another thing which we say is that the rod on the opposite end, which is having a mass capital M and length L, will exert its weight in the downward direction mg, and a tensional force will act on it in this direction, which is equal to T. Now for equilibrium of the system, we can say that it is important that T must be equal to F. So we are saying that the tensional force is equal to the frictional force. So overall we can say that as the thread is not tied with small m, so if there were no friction between the thread and the ball m, the tension in the thread would be zero, and as a result both bodies will have free fall motion. Now obviously in the given problem it is the frictional force exerted by the ball on the thread which becomes the tension in the thread. So now from the condition we can say, or from the language of the problem, if the mass need to get ahead of the or the other end of the rod, so it is important that the acceleration of this mass, if it is a capital M, and for the ball of mass m is equal to a small m, so it is but obvious that acceleration of the rod must be greater than the acceleration of the ball, otherwise it is not possible for the ball to reach the other end of the rod. So now if we apply relative motion equation, that is S relative is equal to U relative T plus half A relative T square. So if we were to use this equation, we can write that the displacement relative is equal to L. The initial velocity of both the system is equal to 0. So we ignore this part and then we get half acceleration of capital M mass, that is rod, minus acceleration of bead into T square. So this is how we frame this equation. Now the next thing that we move ahead with is we apply Newton's law for both the masses individually. So acceleration of the mass m is small m and for the rod is a capital M. So if we write a Newton's law equation for both of them, so we can write the equation in this way, that a weight mg is acting in the downward direction. It is balanced by the frictional force or the tensional force, and it is equal to m into am. So this is the first equation that we can write for the rod. And if we write for the smaller m mass, so we write that mg is acting in the downward direction, which is balanced by the frictional force between the bead or the ball and the thread, and this is equal to m acceleration of small m am. This is for acceleration of capital M, this is acceleration of small m. So this is the second equation which we have. Now apart from this, this is the relative equation which we number it as equation number 3. Now from both these equations, it is very simple for us to obtain the value of f. So on solving, we will obtain, the question is asking us to calculate the frictional force. So on solving, we can obtain that f is equal to twice of L capital M small m upon m minus m T square. So this is how we substitute to obtain the value of frictional force for this particular problem. It is important to note over here that both the masses are moving in the downward direction and the relative value of acceleration is equal to acceleration of capital M mass minus acceleration of small m mass.